can you briefly introduce all of us to what GPUs are, what they do, why they are important, and then as you unfold that story, can you also talk about okay, what's the firmware part and what's the device drivers part? Hey all, welcome to another podcast, and this time around we have Praveen with us, and Praveen, as we know him, is an expert on GPUs. So Praveen, can you maybe go ahead and introduce our audience to your history, work with GPU, and things of those nature?
Right. I'll keep it brief. I started in 2008. I started working in Samsung. Since then, I've been writing embedded code, and I started working on Android. There, I worked on Android BSP, Linux device drivers, some bit of power management, USB, things like that. And most of the work that we were doing in my early career is shipping products based on Exynos SoC of Samsung. Then Intel happened in 2014. I joined Intel, and I was fortunate to land into their GPU team. Although it was just a coincidence, I didn't choose GPU as my field. But then that was a great learning working in Intel for close to 7 years.
Mm-hmm.
Worked on their Linux device driver for GPU. I worked on their GPU firmware. I got a lot of insight into how GPUs work, why they're in the industry, and why do people all around the world, knowingly or unknowingly, they're using. So that was great, and I met you beautiful folks in 2021 when I joined Google, and since then it has been fun working with you guys. I also work on GPU here at Google, but for a third-party GPU that Google integrates in their products.
Right. So, one of the things I kind of did not mention earlier is that, Praveen is not like a stranger to us. He has been with us for like 3 years now. 3 years is accurate, right? 21 is when you had joined. And, we have many coffee discussions around, okay, how X part of the hardware works, how Y part of the hardware works. And usually, GPU is like the beefier of all in terms of, hardware accelerators. So Praveen, maybe let's talk about, so I want this conversation, let's say I'll just lay out like how I was thinking we should structure it. So you briefly mentioned about obviously GPUs, but then firmware on GPUs and device drivers for GPUs. So maybe let's do this. Can you briefly introduce all of us to what GPUs are, what they do, why they are important, and then as you unfold that story, can you also talk about okay, what's the firmware part and what's the device drivers part?
Yes. Let's take it very fundamentally, right? We don't need to understand what GPUs are there for, like the whole graphics pipeline and what
Mm-hmm,
AI
mm-hmm,
ML that GPUs are executing around us. But then, if you look at a fundamental unit of compute, ALU is something that everyone would understand, I feel. So take an ALU, which is just doing some mathematical operation on two integers or floating point numbers, right?
mm-hmm,
So if you take traditional CPUs like Cortex-M7 or something, it has two cluster of ALUs.
mm-hmm, mm-hmm.
One would be for SIMD instructions. It would have a cluster of ALUs which will do in a single instruction. It would run multiple ALUs to perform multiple mathematical
Right,
operations.
right.
If we look at it from that perspective, what GPU brings on the table is the parallelism in terms of these mathematical operations.
Mm-hmm.
Now, to
Okay.
expand it slightly further for our audiences, is think of a matrix multiplication of two matrices which are of the size 4 cross 4, right?
Mm-hmm, mm-hmm.
And slowly increase the size to 16 cross 16 or
Right.
2 cross 32. So your Cortex M7 would be able to handle, as we are nearing the number 32 cross 32 or maybe 64 cross 64 easily
Mm-hmm,
without any inefficiencies, right? But
mm-hmm.
let's go to a matrix that you want to multiple has the size of, let's say, million cross million.
Ah,
What would
okay.
happen in such a scenario, right? If you because data is the new oil. If
True.
you look at it, right, the whole industry is marching towards consuming a lot of data, processing a lot of data,
Right,
and it's
right.
evident that you would see such scale of data, and we
Mm-hmm,
do, right, in real life. So GPUs have these cluster of ALUs. They are sometimes called cores.
mm-hmm.
Core does not even have 100, but maybe thousands of ALUs.
Okay, one core you're saying.
Yeah, and
Okay,
multiple such cores exist in a single GPU hardware,
okay, okay.
and that is the amount of parallelism that GPU offers for a
Mm-hmm,
computer, right?
mm-hmm.
So So that's what a GPU is in summary. So that's the kind of advantage that GPU brings on the table.
Right.
It's massive parallelism in terms of compute operations that you want to perform.
Hmm.
Uh,
So
that
Praveen, I just want to kind of reiterate what you've said, just so that the audience can follow along, and also you can correct if I've got everything right. So what you mentioned was we should look at GPUs from the lens of obviously massive computations on data, and one of the operations that you're not one of the operations, but the class of operations that you're suggesting is matrix manipulation, and then you're oh wait, we also have Nikhil here. Hey Nikhil.
Are we live or recording
Yes,
already?
welcome.
Okay, great.
Yeah, so I was just reiterating what Praveen mentioned about GPUs. So the context that we are supposed to see GPUs in, the light that we are supposed to see them in, is that of number crunching, but operations to be done on matrices specifically. And what you then mentioned was GPUs would have a lot of cores, and each core would have a lot of ALUs, and each ALU is capable of doing like simple operations like add and maybe add and multiply, right? And then we were also saying that once we talk about let's say 1 million by 1 million size of a matrix, that's when the well, the processors give up, the SIMD processors give up at the maybe let's say 32 cross 32, and GPUs we talk about them once you're talking about 100 cross 100, 1000 cross 1000. Does that, is that a good summary?
of course, this is.
Okay, perfect.
And to follow through your earlier question that you also asked me to talk about, after we understand at a high level what this GPU is, what is the device driver, what is the firmware, and what is the stack looking like.
Hmm.
So to summarize real quick, there'll be some data crunch, whether it is a graphics data or a
Hmm.
GPU data, will
Hmm.
be flowing through your user space, right? There'll be memory allocations involved. You have to continuously allocate, deallocate memory, retire the memory once the
Hmm.
operation has been done. So that has to be taken care by some memory management unit, right?
Hmm.
So and then you have to maintain the pipeline of operations that you want to do with the GPU. So there
Okay.
is all the workload that you have to submit, right? So, so these kind of functions will be taken care by your device driver and
Hmm.
firmware put together.
Okay.
Firmware may be taking care of the scheduling that could potentially happen on your hardware, right?
Hmm.
Or if there are virtual machines that are running in the hardware, taking and collating the work coming from all the virtual machines based on their different priorities, that is the part that firmware can take care.
Hmm.
We already talked about device driver, and the user space libraries are pretty much standard libraries like OpenGL,
Hmm.
OpenCL. Many
Right.
of us would have heard, or maybe not, about their names.
Right.
In the Microsoft world, it is DirectX probably, and
Right.
Metal in Mac ecosystem. So all these libraries are responsible for connecting this GPU low-level infrastructure to a
Hmm.
user programmable APIs.
Okay. So again, to read it, you're suggesting that the GPU hardware itself might actually have a firmware on it, right? That is dispatching, let's say, the given computational load on different ALUs.
Not
And
necessarily, but yeah,
okay,
it could have. Most of the
fair.
recent GPUs have.
Okay. So then the firmware then sits on the GPU as a hardware. So there is some management CPU there that is taking care of like the ALUs, distributing work, maybe scheduling work, whatever. But then the GPU gets its work from the device drivers, and that's like the GPU device drivers, which are let's say on Linux or Windows or Mac. And then you're suggesting that on top of that, those drivers are the user space libraries like Metal, DirectX, or OpenGL, and that is what the user is actually using, like the games, or maybe in case of people who do AI, they're using those libraries to deploy the workload.
Right. And we
Okay.
can also go through a typical graphics
Hmm.
pipeline,
Hmm.
right? For everyone to understand
Hmm.
what really happens in terms of what does it really take for somebody to, you know,
Hmm.
just take some raw data representation of a 3D scene
Hmm.
and convert it into a displayable frame buffer, which is probably whatever that can be displayed on your 2D surface, like your
Right.
display, TV, monitor, console. These,
Right.
yeah,
Yeah,
So.
it would be nice if you could go through different aspects of like just take a use case like as you mentioned game, and like
Hmm.
translate different software stack, like the games, actual games, game engines, libraries, how it gets translated to lower level details like shader language.
Right.
Mm-hmm.
Uh, for the time that we have scheduled for this podcast, let's just take a generic case in this, right?
Right, right.
So, how do you describe a 3D scene, right, in mathematical terms, right? So, what it could mean that you have your x-axis, y-axis, and z-axis. So, let's take a primitive. Primitive is nothing but a geometry, right? An object per se. Uh, so you put that in that coordinate space that you have. Now, with respect to that origin that you have chosen, let's say a ball that you have kept somewhere. Now, if you have to draw multiple points on the surface of that ball, you could draw million, thousand,
Mm-hmm. Mm-hmm.
whatever, right? So, and every dot on that you draw could describe the positioning of the surface,
The point on the surface,
point
is
on
it?
the surface,
Fair.
and then it could have multiple different attributes attached to it, right? One is the position itself. Another could be the color associated with it, right?
Hmm.
Other attributes could be depth or multiple more, right?
Hmm.
All
Hmm.
of these parameters are actually well defined by OpenGL standard, right?
Okay.
So that builds a huge input matrix for representing a 3D scene. Now,
Hmm.
if this is clear, we can move forward in a simple, pipeline, graphics pipeline, right?
Hmm.
What would happen in that graphics pipeline that you are just giving this representation, the 3D representation of an object, and it finally renders a 2D RGB, YOV, or NV12. These are the different formats. Don't worry if someone doesn't know about these
Hmm.
formats.
Hmm.
These are the formats in which an image is displayed on your display. Right? Most of the displays, new age displays, you work with these formats. So how does that pipeline take this raw thing, does some magic, and generates that RGB image for you?
Hmm.
So there are different stages of pipeline that it has to go through, right? So we will quickly cover that.
Hmm.
There is something called vertex shader stage, right?
Hmm.
Which could help in terms of transforming the vertices that you have selected, right?
Okay.
So,
So, Praveen, I just want to kind of intercept here and just quickly recap what you mentioned. You mentioned that the graphics data, the position and details of different objects are provided as, let's say, vertices,
right,
points on the surface, and then there is associated details with each points, like its color, its shade, maybe its like depth, whatever, those kind of things. And then all these data is being fed to the GPU, and from there you're now making a case as to something will be done with it.
correct.
Okay.
You could potentially build this whole graphics pipeline in a software, right?
Hmm.
You
Hmm.
don't need GPUs for it, but
Hmm.
then you will hit a limit
Hmm.
at which you will be saturated in terms of, hey, to generate a 4K frame, it's taking me days.
Fair, fair,
Maybe,
fair.
right? So what GPU brings in the table, again, the parallelism and massive compute power, where
Hmm.
uh, all the shader stages or different stages of these pipeline that we are probably about to talk about, right? So those are accelerated through GPU hardware,
Hmm.
right? So GPU hardware at every stage of this graphics pipeline will come handy in terms of finishing that work on millions of vertices or millions of data that you are providing in a jiffy of time. While
Okay.
if you do the same operation using a traditional CPU, it could take like much more time.
Right. Minutes and hours, kind of. Right.
So,
And
so,
even days.
so since we are talking about the hardware, so since you mentioned that there are numbers of ALU units in a particular core, and then there are hundreds of core, right?
Right.
So I wanted to ask one question. So what is the difference between a normal CPU ALU unit and a GPU ALU unit? So is the GPU ALU unit is customized for some workload execution, or it's just a generic, and then you are combining too many so that speed up the processing?
Right. So I think ALU is just an ALU,
Mhm.
whatever operations that. So they could also probably optimize it for a certain operation that happens frequently on GPU hardware, right? I might not have all the details right now. Another thing that this ALU is very specialized about is the operations happening on floating point numbers, right?
Hmm.
Precision with the floating point numbers. So that's the USP, I would say, of the GPU values. And I just want to correct in terms of we have hundreds or thousands of ALUs sitting in one core, and depending on the GPU performance or the size of the GPU, we could have like different cores. Uh, I think the computation power of the GPU is talked about in terms of flops,
Hmm.
megaflops, gigaflops,
Right.
kind of thing, like floating operations per second, something like that. Yeah. Uh, okay, so I hope that answers the question to a certain extent.
Yeah, yeah,
Okay, so let me remind us. So we were talking about different stages. There were, the image was submitted, not image, but the data of the scene was submitted as vertices, with each vertex having details associated with it. So go
Correct.
ahead, Praveen. Can you now talk
Yes.
what happens to it? Yeah.
So yeah, I mean, there are a number of things happening in this pipeline. So we'll just look at the key part of this pipeline. This vertex shader, right? So which does the geometric, the vertex transformation.
Hmm.
Transformation is like maybe the coordinates that has been given to you for a shape is with respect to an origin where the observer is not sitting, right?
Fair,
Like,
fair. Yes.
like, so if this is my origin, maybe my observer is here, right?
Hmm. Hmm.
So I will have to transform each and every vertices with respect to the observer, right?
Hmm.
To understand how would that object look from this observer's point of view, not through this origin.
Hmm. Hmm.
So probably vertex shader takes care of this mathematical. It's a huge mathematical operation to transform all the
Fair.
vertices to the
Fair.
new origin, right? And then there is something called tessellation, right?
Hmm.
Now, yeah, all of us understand the 3D space, but then the smallest primitive or smallest shape, I would say, in which you could represent a 3D is three dots, a triangle, right?
Hmm.
They're
Okay.
coplanar, right? Now, what we do with all of these vertices, we would like to convert them into smooth surfaces of triangles, right? Like imagine a whichever small triangles with the adjacent vertices you could draw,
Hmm.
right,
Hmm. 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 Hmm.
on a ball, right?
Right.
So each triangle, if you so the reason why these triangles are drawn is like you will probably compute the overall look and feel of that triangle, right? Once
Hmm.
you have computed each and every triangle that is positioned on that
Surface.
particular surface, I think your 3D rendering is complete, right?
I see.
With respect
Okay.
to all the vertices that are provided. That is the tessellation.
Right. So this kind of reminds me that in animation, people have this like wireframe, and there is always like a triangle involved there.
Correct. Yeah.
So what you're suggesting is that the 3D surface is represented obviously by points, but
Right.
then it's like 3 points at a time. You can draw like triangles, and then the entire surface is full of triangles,
Correct.
and the GPU helps you render that triangle.
Yes.
And then at some point, you were mentioning that the position of that object is like represented using some origin, and with respect to that origin, the observer is put at some coordinate.
Right.
And then, if I'm understanding this correctly, the GPU is supposed to render the 2D flattened image as seen from that point of view. Okay,
Yes.
perfect. Perfect.
And you could again transform
Hmm.
the observer to some other region next time, and you would
I
have to
see.
create the whole scene again.
So what I'm understanding then, let's say if there is a game scene going on, and let's say like first person, a third person shooter game, right? So then what's really happening is all the objects are being like positioned at some coordinates with respect to some origin,
Yeah.
and then we are moving really the observer, and GPU is rendering like how the scene would be as seen by the observer. Right.
Right.
Nice. Very, very, very cool.
But then GPU does the computation for the part of the object that is not visible.
Oh, okay. Wait.
Right.
What you? I think I understand what you're saying. So if there was like a bottle and a plate behind the bottle, you're saying it computes the plate and also the bottle.
Right.
Wow. Okay.
Yeah, it
Okay.
does. But then only during the final rendering of the 2D or somewhere before it, it would realize that, hey, bottle is coming in the front. So, you know,
Hmm.
unless it is a clear, non-opaque,
Right. Transparent kind of thing.
transparency.
Yeah.
transparent field, you would not be able to see. So all these parameters are already given to you in terms of those vertices, right? So then comes the geometry shader, right? So geometry shader is basically that smooth triangles that we form.
Mhm, mhm.
I think that will create that geometry in terms of filling in all the necessary details uh, to make the geometry look like a 3D. And then finally comes the rasterization, which is very important stage. The rasterization basically converts all of this computation that we have done into your actual pixels, which you could put into the memory, probably give it
I
to
see.
the unit, right?
I see.
Yeah. So
So all of what is happening before rasterization, and I suppose I should also mention, like I had this doubt. So when you mentioned that, it'll kind of decide which details to discard based on, what object is behind or in front of which object, and also if the surface has to be transparent or not. So is the surface being transparent and not, that is also encoded as part of the pixel, not pixel, but the geometry data, the vertices data that we talked about?
right. So there is something called texture.
Ah, nice. Okay, I was going to
Yeah.
pitch that. Is that texture? And
So there's a
okay, it
texture
is.
data also provided. Let's say you are drawing cat, right?
Hmm, hmm,
So so all around the surface of a cat, you will have the texture just like the body of a real cat, right?
hmm, hmm.
So you would want to just draw those textures on the final rendered image, right?
Understood.
So they will compute, and then there will be a texture put onto your final
That
image.
object essentially. F- Fair. And then what you mentioned was the rasterization process is the one wherein we'll take that geometry, like process geometry, so to speak, and now maybe convert that into pixel data to be sent towards, let's say, video buffer.
Correct. Yeah.
I see. Nice, nice.
So
Very cool. Very
and
cool.
in a 3D scene, when you're playing a game, it is all happening real time, like frame of
Which is the crazy part.
right.
So 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 what I recall from like some previous experience, that there would be two frame buffer, right? So GPU
Okay.
calculates one, and then another one will be displayed by display driver or something.
Correct.
So
It's,
can you share something about there?
it's called ping pong modeling, right?
Okay,
I see.
it's an interesting model, I guess.
Also,
So
I want to predict. So is it like we have like two buffers? One, the GPU is filling in one, while the video,
Right,
like the display device, is picking from one, and next time around it picks from like
right,
the buffer, second buffer, while the GPU is populating the first buffer.
right.
right.
Man, crazy.
Yes, I want to bring up few things. So there are
Sure.
cases where there's front buffer rendering and there is a double buffer rendering. In the model
Okay.
world, we use this double buffer rendering.
I see.
So if somebody is modifying the buffer, you would not see the half modified buffer. So in the old days,
Ah.
you have this Windows XP where somebody started like drawing a window and like you could see the history of that window.
Okay.
So that is
I
front
understand.
buffer rendering, where basically even while modifying the window was half modified, by the time you rendered it, so if you like move it fast, you would see half
Uh,
was there. So that was
uh,
front buffer rendering. So I thought people would relate to that.
oh, that is nice. Yes.
And with time, all the displays that are out there in the market, they have a very fast refresh rate, right?
Hmm.
How
Hmm.
fast the scene is changing? 60 hertz, 120 hertz now, right? 120 is a very fast refresh rate that you would see in recent handheld devices. Um, and then if refresh rate is 120 and your GPU is
Hmm.
not able to cope up with that,
Hmm.
then it's not a good deal. I mean, you could see
Right.
frame in multiple refresh rates. You could see jerk effect.
So,
Right.
so I heard that there is term frame drop or something, right? So what does that mean? Like the GPU is not able to perform the frame rendering. Is that what is it?
Yeah. So there could be two scenarios if we look at it from. So let's say 60 hertz, right? If you divide a second into 60 parts, so
Hmm.
1 by 60th of a second, right? So if GPU is generating a frame every 1 by 60th second, display is picking up, right? So before every refresh, I think you are flipping the buffer like Nikhil mentioned. It's if we are using double buffer, you are able to flip. So this is called a flip, right? Buffer
Hmm.
A versus buffer B, AB, 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 flip is happening. Let's say
Hmm.
you miss the flip, right? Then I think what would potentially happen is like the same frame going into two, and suddenly you would drop one frame, and maybe if you are seeing frame number 180, you would suddenly see frame number 182 or 184.
Hmm.
You might see that the user experience would not be that great. Like
Hmm. Hmm.
playing a real-time game, and suddenly, if some frames are dropped in between, what would potentially happen if the shooter is shooting and suddenly the
This has happened with me.
so that
Your
would happen.
character is frozen. You think you've killed someone, but well, you're
Yeah,
dead.
yeah,
The
Something
cassette
has
in your
happened.
head.
Yeah. Yeah.
What happened?
But this is very interesting and just to give people a sense of the computation involved here. Let's say we are talking about, for example, 120 hertz refresh rate. So that means 120 frames are to be shown every second.
Yes.
And then depending on what your resolution is, let's say 4K, for example, just as an overkill, right? So 4K pixel values shown 120
It's
times
4K
per
into 2K, so 2 million pixels. So 8 million pixels.
8 million pixels, and then each pixel is like RGB.
8
32
alpha also.
bit.
So you
Yeah.
can
So,
assume
sorry, what was it, Nikhil? Could you
RGB
elaborate?
8. So alpha also.
Alpha also, yes, yes. The alpha denotes the transparency thingy. Is that correct? RGB is like for the color information, and alpha is for transparency. Is that right?
Yeah.
Okay,
Yes.
okay. So essentially, like four other set of information for one pixel. That's bonkers, man. You just have to like multiply, and then it's a huge number.
It's a crazy amount of computation that you're doing every second.
Yeah,
Yeah.
and then the battery on the phone, for example, lasts,
and
which is even more bizarre.
and the crazy part is that after 60 frames, the human's eye are not able to distinguish
16,
whether
16. After 16 frames a second, we can,
okay, but then
well, at least it gives a sense of motion.
right.
Yeah.
But then, like if you scroll very fast, right? In that case, if you go beyond 60, then there is hardly any difference seen by humans. I
Well,
mean,
I don't know.
yeah,
I don't
I
know.
think I might have some incorrect data as well. So,
What
On
I
an average,
know
we say
is
that 1/10 of a second is human persistence memory. But then
right.
hmm,
again, is average human. There are some human who are like,
superhuman.
for them it is no. I mean, it's not like super, but yeah,
Yeah.
for some it is 10 milliseconds, for some it is 8, or for some
Yeah.
it is 14. Or whatever.
Hmm.
You're saying, could you talk to the units here? 10 milliseconds you meant, or 1/10 of
Yeah,
a second?
1/10 I want to say.
Ah,
Yeah,
okay,
1/10 I
okay,
want to
fair,
say. So
fair,
that would be
fair,
100 milliseconds actually.
fair.
I don't
Right.
know, I might be wrong here, but this is what.
Yeah, that's pretty interesting. So it's the amalgamation of your display pipeline with GPU.
No, no, no. This is about persistence of vision. Like if you are seeing something changed, you
Right,
basically
right, right.
increase
Yes.
everything you've seen.
Mhm.
Like I'm talking about persistence of vision. Like basically, whatever happens in 100 milliseconds, you start seeing everything in one shot.
Hmm.
I'm
Like
talking.
you perceive it to be moving image, because like like let's say if my hand is here, and 1/10 of a second later it's here, I would see it move kind of, because there's like some hysteresis of the
Yeah, yeah.
previous
I'm saying
frame.
in that 1/10 of second, if you're like moved a lot of places, I see all of those frames in one shot.
Yeah,
Like
fair,
my
fair,
image,
fair.
my previous.
It's like a blur.
Yeah.
Right.
Right.
Fair, fair. I think I'm getting it. I'm not able to express it. People can, Google persistence of vision. I recall this was like a standard question in class 10th. What's like the persistence of human vision? It's like 116.
Yeah.
Okay. 16 frames a second, essentially.
You
Yeah.
studied your class 10th pretty well. I mean,
Oh,
that
I
makes
did. After that, I was, well, we are going off topic here, but
yes.
11th and 12th class, yeah, grade, whatever. I was introduced to the wonderful world of chemistry, where I saw F block and D block, and I was like, what is this? And I'm
So I
still
just wanted to add one more complication. So we
good.
just are doing some calculation that there is like 4K by 2K image, and that has to be generated 120. If you see, right, if you're just creating like a plain image, then those calculations make sense when you're just like putting red color everywhere. But we have to now also account the fact that there are like millions of triangles that need
Yes.
calculated, and after that you put that like that 4K image. So
Right.
whatever calculations we made, that is like the basic step one. Multiply that with maybe some 20, 30 times, or maybe,
Processing. Yeah, yeah, yeah.
and that is the real job the GPU is doing, depending on how complex the scene is. Maybe
Bit
Praveen, you can, like,
bonkers.
take an example, like a typical game, take a scene and like just estimate.
Nikhil, I have to suggest that we were talking about exactly the same thing behind the scenes with Praveen. And there was like a limit as to which we wanted to peel the onion in this podcast. What we realized was, let's have a workshop that talks about GPU in
Yeah.
all these details. So Praveen, if you want to speak to it, go ahead. But feel free to not peel the onion completely, because I think it, at least
Yes.
for me, it will be too much.
Right. It would go back to the same pipeline again, right? I would say, which we just discussed, like your vertex shader, your tessellation, your geometry shader, rasterization, fragment shader, whatever different stages are there. What I could also tell is like some of these are programmable units, some of these are
Mm.
fixed functions, right? So your GPU hardware might have these segregations. So some of the things are programmable, which are given to your ALUs that we talked about. Some of these things could be some fixed function hardware sitting next to those ALU clusters, which will just do that program, the fixed job in this pipeline. And the whole pipeline can be accelerated through hardware. So that's what really happens in real time. And another thing that I want to cover in terms of that generating 60 frames per second or 120 frames per second. So what efficient GPUs would do probably is they would generate these frames fast enough in like three-fourth or two-third time of a second, and remaining part probably when they can go to sleep, and that's how they can save the power.
Wait, you're saying in between frame rendering, GPU can also go to sleep?
It could if the what I would say the computation capacity of the GPU is
Ah, I see, I
far
see.
better than what is expected out of it in terms
Understood.
of every
Understood.
second compute.
Right. I think I understand it now. It's like it need not, well, in a game like situation where a game is on, maybe this GPU is like continuously busy,
right?
but in other cases the workload on it would be like so tiny that it could just render it fast and then go in low power state. Okay, that is understandable. Fair.
So let's say some videos are being played, right? In that case, since it knows, okay, this is the video I need to render for, let's say, next 10 seconds, right? Then I think it can do that and then go into the power.
Hmm.
Uh,
Also, does the GPU render thing? How do I put this? Does the GPU reuse the previous render? Like, for example, let's say there is a scene where the motion is going to be like just straight. So can it use like a lot of previous render that it has done and only account for the delta change? Does that happen?
Yeah, that could happen. I mean, that
It's
somehow puts some sort of an efficiency here.
yeah, okay, fair, fair. But
So
that does happen.
that should be happening because it doesn't make sense to create the whole scene again if you
Hmm.
have only portion of the scene changing where you want to compute the data. I
Hmm.
think it would make more sense to just compute the portion and just keep the rest of the scene same.
I see.
So I
Fair.
want to focus on the fact that, like you mentioned, that there are like thousands of CPU cores. So in terms of compute power, most of the time the GPUs are much powerful than we actually think. Most of the time, limitations come into the fact that they cannot access the data as fast as they want. So they are,
The memory is the
and
bottleneck.
maybe Praveen, you can talk about, like, people talk about 4 GB
Uh,
graphics card or 8 GB graphics card. Why? What does it mean and things like that.
Uh, so wait, I just want to forward project. What you're saying, Nikhil, is the GPU is like super ultra capable, but if your memory is slow, none of that efficiency matters.
right.
Correct.
Oh, go,
Exactly.
go ahead, Praveen. Yeah.
So for that matter, I mean, we can do everyone can do this exercise at home. Just think of 4K frames, right?
Hmm.
The size of a 4K frame. Just figure out what the size of a 4K frame
Fair.
is.
Hmm.
It's homework for
Hmm.
people who are interested. And then let's say you are rendering 60 frames per second, right? So
Okay.
compute how much of a data would GPU have to write back to the memory. Forget about the reading part. That is anyway happening. It's a two-way street, right?
Hmm.
So how much of a memory bandwidth it would require in terms of, let's say, I would say GBps, and the answer would come in terms of GBps. So think about it and how fast your memory have to be in order to support this, right? And we are also talking about 8K and 16K as well in terms of frame.
Right.
Right?
Right.
So what would those GPUs do? And in this is the graphics pipeline. When it comes to data, the story is totally different, right? So I mean, today scenario, I mean, the LLM models, right? So whatever computation power that you get from GPU is less only. I mean, it's not enough, right? So that's what that we are living in.
This is very interesting, and I see that we're nearing the end of our scheduled time, so we have about like 3 minutes. But one of the questions I wanted to ask you was, can you speak to the relation of GPU with AI? And maybe we can close
Yes.
on that. And as we maybe later do the workshop, we can update the video description with the link to that workshop.
Yes.
Uh,
So similar question I had, that since, as it name suggests, right, it's for processing the graphics, right? There is an observer, there is an image, there is objects. How do you render, right? So now, how come you use it to
Do
execute
AI?
the workload execution, right? So
How does the Nvidia stock go up?
right.
Right, right. So it was accidental, I think, somewhere in NVIDIA only. At one point of time, they realized that if you have a large data to do some computation on, and you have these ALUs, multi-cluster ALUs sitting inside your GPU, why don't you try it? And then this was an accidental use of GPU for high complex compute, and that
Hmm.
was accidental, and there was no looking back since then. Then multiple compute libraries came up. I think CUDA is
Yes, CUDA is something I'm aware of.
OpenCL is very industry wide,
Standard kind of popular. Okay.
and Tensor is another framework that within Google that we use. I think it might delegate the work to OpenCL at one point of time, but yeah, this the TensorFlow. Uh,
And there is, I think, also PyTorch from Facebook, if I'm not
Correct.
wrong.
Yeah. So all of this would have to somewhere pipe and channel their work in terms of compute to the GPU in the same manner that we are doing for graphics, right? But here, most of the work has to happen on those ALUs that we talked about.
Hmm.
The fixed function part of the graphics pipeline is maybe not much used in the AI ML world, but then for your operations in terms of matrix multiplication, convolution, another floating point operations that you want to perform on your data,
Hmm.
all of those things super parallelized and efficient on GPUs is is what makes GPU very very powerful and useful in this endeavor. And I think yeah, that's just
so
a summary for 3 minutes, I guess.
so do they remove this GPU pipeline part for the AI GPUs, or like it's the same instance being directed for two different workloads?
Right. I don't have an answer for that, but what I can tell you that a lot of companies, including like big shots like Google, Microsoft, they are moving towards developing their own hardware, their own silicon
Right.
for efficient compute, right? So
Hmm.
so they are doing it as we know, and the reason why they are doing it is they know that there is a part where we can bring efficiency, we can control
Hmm.
it end to end, we can build the whole software ecosystem around the same hardware that we want to build, and that is nothing different from the ALU clusters of GPUs that we are talking about. It's doing pretty much the same thing. They would just want to efficiently implement it on the kind of computation that they are doing with that hardware.
Fair, fair. That makes sense. And that kind of then tells me that talking about AI accelerators is maybe something we can take up next time. And talk about, okay, why would you in like what efficiency do you really bring when you go from, let's say, GPU to a dedicated AI accelerator?
Yeah.
So maybe if there are no more questions, I'm thinking we can wrap up this podcast and politely end it. And again, for our audience, we plan on having like a GPU related workshop where we'll go from like the basics to the advanced. And the link for that we'll just append it in the description, video description. So hopefully you like this. And does anyone have any questions at this point? Okay, there is no. And we'll okay, not peel the GPU onion anymore for this podcast. We'll just wrap it here and see you folks next time.
Yep.
Thank you. I hope it was good.
Yeah.
Um,
Yep.
Yeah.
I had a good time.
Yeah.
Thank you so much.
Yeah.